So good morning. I'm Jen Whitman, Director of the Division of Safety Systems in NRR, your session chair for today. So I'll take care of a couple of housekeeping items. Ensure your devices are silenced, and if you need to leave during the session, please try to do so during a natural break. We'll be handling all of the Q&A electronically for both in-person and virtual attendees. So you can go ahead and scan the QR code when it comes up, and that's how you can input questions. If you're joining us virtually, you should see a tab for the Q&A. All questions go into the same queue so we can see everything in one place. And this is also a reminder that all sessions are being recorded. So with that out of the way, I'd like to thank everybody for joining us today. While I am new to the DSS director role since the last RIC, I'm not new to the ATF effort. I was involved in its early stages nearly a decade ago, clarifying regulatory requirements for lead test assemblies, supporting planned ATF irradiation campaigns. And I also supported the initial development of the ATF project plan. Since then, the program's expanded beyond new fuel and cladding technologies to include higher enrichment levels and higher burnups. More recently, legislation and policy directives, such as the ADVANCE Act and Executive Order 14300, have reinforced the NRC's role in enabling the safe and secure use and deployment of civilian nuclear energy technologies through efficient and reliable licensing, oversight, and regulation for the benefit of society and the environment. At the same time, growing electricity demand and incentives for power generation have increased interest in power uprates and extended operating cycles, both supported by the fuel innovations we'll hear about today. Returning to the ATF program as the lead division director, I'm encouraged that a practical and efficient licensing framework for near-term commercial deployment is nearly complete. Taking leadership of this major program just as it nears successful completion is admittedly a great way to take credit. But joking aside, this progress reflects the work of so many people both inside and outside the NRC, including several represented on this panel here today. Within NRR, staff from 4 different divisions collaborated to develop guidance, conduct licensing reviews, and propose regulatory updates addressing key technical issues and regulatory challenges associated with in-core operations for planned power uprates and extended cycles over the next 5 years. NMSS staff addressed regulatory and licensing issues related to the front end and back ends of the fuel cycle and supported environmental and rulemaking activities. Research partnered with both offices to develop strong technical bases for resolving key issues. You'll hear more about recent accomplishments from the panel. DOE and NRC engagements have also helped NRC develop early understandings of technical issues and take proactive steps to ensure they're resolved. Finally, industry and stakeholders have contributed through numerous public engagements to ensure that the emerging regulatory framework reflects practical licensing needs. By the time of the next RIC, we expect to complete the major goals of the original ATF project plan. Our focus will then shift to implementing those licensing pathways to support commercial deployment of those technologies, as well as the power uprates and extended cycles that they enable. But borrowing a line from Steve Jobs, one more thing. This is not the end. The NRC, DOE, and external stakeholders are already discussing new technologies and licensing approaches to enable power uprates in the 2030s and greater operational flexibility without compromising safety. Examples include risk-informing certain events, addressing time at temperature considerations, and exploring longer-term fuel cladding concepts currently being researched. Work is also ongoing to support advanced reactor fuel and high-assay low-enriched uranium. I'm confident that the same collaboration and commitment that brought us this far will help us achieve these ambitious goals. And so now I'm going to go ahead and introduce each of our panel members for today. We've got an exciting session for you, and we'll start off with Mr. Chris Van Wert, who serves as Senior Technical Advisor in Nuclear Fuel in the Division of Safety Systems in NRR. He joined the NRC in 2007 as a reactor systems engineer in the Office of New Reactors. He served as lead technical reviewer for the AP 1000 design certification and multiple fuel rod design methodology and spent fuel pool criticality topical reports. After joining the Division of Advanced Reactors and Non-Power Utilization Facilities, he served as the technical team lead for Terrestrial Power's molten salt reactor and the Abilene Christian University molten salt research reactor construction permit. Before joining the NRC, Mr. Van Wert worked as a senior engineer for Westinghouse in the fuel rod and thermal hydraulic design group, and Mr. Van Wert received a bachelor's and master's degrees in nuclear engineering from Purdue University. Next, we have Mr. Jason Piotr, currently serving as the acting branch chief and team leader of the new fuels activities, including ATF and advanced reactor fuel in the Division of Fuel Management in NMSS. Jason joined the NRC in 2004 and has held various technical positions within the agency, including senior technical reviewer in structural, thermal, and containment disciplines in the Office of NMSS and the Office of Research. He received a bachelor's in civil engineering from the University of Iowa and a master's in structural engineering from Virginia Polytechnic Institute and State University. Then joining us virtually will be Dr. Nathan Capps, a senior staff scientist at Oak Ridge National Laboratory in the Nuclear Energy and Fuel Cycle Division's Fuel Cladding and Core Internals Group. Dr. Capps' research seeks to transform and accelerate nuclear fuel deployment, qualification, and licensing by exploiting advanced performance phenomena and address data gaps or uncertainties. Coupling this approach with in situ data collection during targeted experimental testing is expected to greatly reduce the time required. In addition to his scientific achievements, Dr. Capps leads and supports strategic industry engagements to sustain and advance the existing light water reactor fleet by deploying accident-tolerant fuel with increased burnups. This has led to extensive experience working with private industry, nuclear reactor owners, national laboratories, and academia on multilateral projects aimed at addressing critical barriers to the safe and economical expansion of nuclear power. These engagements extend to supporting licensing efforts by serving as an independent consultant to the NRC and leading nuclear fuel vendor qualification plans. Dr. Capps' efforts have resulted in the development and application of licensing approaches to address gaps preventing burnup extension. These approaches have informed nuclear fuel vendor licensing methodologies and the confirmatory approaches of the NRC. He holds numerous leadership roles within the U.S. Department of Energy, Office of Nuclear Energy, and serves as an expert consultant for the International Atomic Energy Agency. And then our final panel member for today, Mr. John Harrell, is Director of Dominion Energy's Nuclear Analysis, Fuel and Regulatory Assurance Department. He supports North Anna, Surrey, Millstone, and VC Summer nuclear power stations in the area of nuclear fuel procurement, fuel engineering, and nuclear safety engineering, corporate nuclear regulatory affairs, and emergency preparedness. John has served at Dominion Energy since 1987 in a progression of corporate and station engineering, staff, and management roles. His early technical work included safety analysis methods development, reactor core thermal hydraulic design, accident and containment analysis, reload cycle management, reactor vessel materials, licensing applications, and resolution of as-found safety-related plant equipment conditions. He earned a bachelor's and master's degrees in nuclear engineering from the University of Virginia and an MBA from the University of Richmond, where he taught management from 1995 to 2000. John chairs the Virginia Nuclear Energy Consortium Board and the Virginia Innovative Nuclear Hub Board, and serves on the Virginia Commonwealth University's Nuclear Engineering Program Advisory Board. At Dominion Energy, he is a member of the Management Safety Review Committee and is a corporate response manager for emergency response and has been management sponsor of the Nuclear Analysis and Fuel University Partnership Program since its inception in the 1990s. So with that, I'm going to turn it over to Mr. Chris Van Wert to get us started.
Thank you very much. Thank you for the introduction. So, good morning. I'm actually very happy to see we had the turnout we did. I was a little bit nervous being on the third day and last day of the RIC and the early session, I thought I might be looking at an empty room, but I'm actually very happy to be here and actually see some faces here. So thank you very much for sticking it through and showing up this morning. As already stated, my name is Chris Van Wert, and I'm the Senior Technical Advisor for Reactor Fuel in the Division of Safety Systems. And I'm very excited to be here with you today to discuss a little bit about some of the advancements in nuclear fuel and how the NRC is revising our regulatory review strategy to be able to efficiently review these novel designs and maintain our focus on public health and safety. Next slide, please. So there's kind of a convergence of multiple things happening right now that's allowing for these advancements in fuel designs to be realized quicker than previous timescales had normally dictated. The first change is that nuclear power is increasingly seen as a national priority. This is demonstrated through multiple executive orders that came out in 2025, but also before that, things like the Advanced Act in 2024, and before that even NEMA, which was, I think, the late teens. Additionally, the industry has been quite busy over the past several years developing new technologies, and these are used to support increased safety and more efficient fuel management strategies. And last but not least, there's been a lot of efforts related to improving the regulatory processes and guidance to enable efficient evaluation of the expected new fuel technologies. I'll speak to each of these in the upcoming slides. Next slide, please. So in recent years, there's been an increased understanding nationally regarding the important role that nuclear power can play in meeting our ever-increasing energy demands, while at the same time not contributing to the additional greenhouse gases. There's been several executive orders released in 2025 that touch upon nuclear power, but the two I wanted to highlight in this presentation are Executive Orders 14300 and 14302. 14300 at its heart is an overall call for the NRC to modernize its regulations and licensing processes to facilitate deployment of new technologies and expand the American nuclear energy capacity. This executive order has led to substantial efforts to look at our regulatory practices and our rules and guidance, and to provide updates where necessary to enable an effective review without overly burdening the process, especially when those older regulatory frameworks were based on the older technologies. Executive Order 14302 is directed more at the Department of Energy, but it does establish a goal of 5 gigawatts of power uprates to the existing fleet. This would require a substantial review effort by the NRC, and the NRC has therefore been working to develop a more efficient review process to enable a quicker review while ensuring the safe generation of additional power from the existing reactor fleet. Another example of how nuclear power is seen as a national priority is the passing of the Advanced Act, which was intended to accelerate the deployment of new nuclear reactors, reduce regulatory costs, and to accelerate the deployment of and to strengthen the U.S. nuclear supply chain. The Advanced Act directs the NRC to strengthen the readiness for advanced nuclear fuels by assessing preparedness, deepening coordination with their partners, and focusing on key research needs. A report which goes over how the NRC is achieving these goals will be available later this year. Next slide, please. So there has been a lot of effort put in by the industry to develop improved fuel designs that are better able to handle longer cycles, higher power, and accident conditions. DOE has been instrumental in supporting this development of accident-tolerant fuels. There are three main technologies that are either approved or expected to be completed in the near term, and these include coated cladding, doped pellets, and increased enrichment or higher burnup. Coated cladding increases the fuel reliability and safety margins, and this in turn provides more operational flexibility. Coated cladding provides enhanced protection of fuel rods against debris fretting and offers corrosion resistance and superior material behavior over a range of conditions. Doped pellets increases fuel safety and increases fuel density under certain conditions, and it does this by realizing larger ceramic grain sizes, and this promotes fission gas retention within the pellets themselves. This can reduce the fission gases that would be released during a postulated accident. Increased enrichment and higher burnups provides increased energy per batch of fresh fuel, which allows for the cycle length extensions, fewer spent fuel assemblies, and additional power uprates. Together, these technologies offer increased fuel performance, higher accident tolerance, and less spent fuel waste while providing greater operational flexibility for the licensees. Next slide, please. The NRC initiated rulemaking in response to the directives found in Executive Order 14300, and this effort includes major updates and revision to existing rules and to develop new rules in order to remove unnecessary barriers for the licensing of new technologies. Many different areas were addressed in this rulemaking effort, but some examples that relate to fuel include removing barriers for increasing U-235 enrichment to values greater than 5%, and the proposal of new performance-based risk-informed emergency core cooling system rule. That last one does sound familiar, I'm sure, to a lot of people in the room here because it's been around for a little while, but this time it's actually being implemented under the Executive Order 14300 rule. Another major undertaking is related to licensing efficiency. I won't go into great detail here because there's another presentation by Michael later this, I think it's later this morning in TH18. I don't want to steal his thunder, but suffice it to say that we are developing new power uprate licensing processes with a graded approach screening. These improvements to the regulatory framework will help make the licensing of novel technologies easier by reducing the prescriptive aspects of regulations, which are based around the existing light water reactor fleet and traditional operating conditions. By adopting a more risk-informed performance-based approach, the NRC licensing process will be quicker while maintaining its focus on safety. Next slide, please. Another example of recent efforts to improve regulatory readiness is the work by the industry and the NRC to address concerns of fuel fragmentation, relocation, and dispersal. Two methodology topical reports address this issue and are nearing completion of the review. EPRI's alternate licensing strategy and Framatone's increased burnup of pressurized water reactors. In addition to the industry's submittal and the staff's review, the Office of Research at the NRC has performed an analysis to investigate how dispersed fuel affects PCT calculations. Previous efforts identified different methods to model fuel dispersal, and this new work leveraged that while also performing analysis with trace to determine how it affects the PCT. And it was found that for the study that we looked at, it was found that the PCT was not significantly impacted. However, the duration of the event was extended. I want to stress that this was not an all-inclusive analysis. This was a singular analysis, but we were using this to get a better understanding of what we might expect. In summary, while there's a lot more to be learned about FFRD, the NRC has demonstrated that it is currently ready to perform technical reviews of methodologies for addressing FFRD. Next slide, please. And dose is another area that has received a lot of effort to provide regulatory guidance to support the desire for increased enrichment and higher burnups. Revision 1 of Reg Guide 1.183 on alternate source term was released in October of 2023, and it added guidance for accident-tolerant fuel and increased enrichment source term analyses. Additionally, it supports up to 68 gigawatt days per MTU and added transient release fractions. Revision 2 is currently under development, and it supports the use of fuel enriched up to 20% and burnups up to 80 gigawatt days. Next slide, please. So, while a lot of the progress has been made, the NRC is continually looking for ways to improve the licensing process to avoid unduly burdening an applicant while still ensuring a high level of safety. The staff is looking at potential future challenges to help identify rule and guidance changes early. Some examples include potential extended power uprates that go beyond the current licensing experience, new core and fuel designs and operating strategies that develop after the Executive Order 14300 rule goes into effect, potential increases in FFRD, and the use of time and temperature and accident analysis methodologies. These are just some of the areas that we're currently thinking about and trying to decide the best approach to handle. Next slide, please. So I do recognize that in the normal bottom line up front presentation style, that this slide would have been the first one, but old habits die hard, and so this is really more of a summary. So maybe a little bit of a mislabel here, but I did want to stress that, and I'm hoping that the message got through, that we have already resolved or will resolve imminently the technical issues for near-term industry plans. And we have also succeeded in identifying efficiencies in the licensing process and are currently finalizing related improvements. We're also currently updating the regulatory framework to align with the above and expect a completion date towards the end of the calendar year. Last but not least, we are also looking ahead to see what sort of long-term industry plans might be and to critically look at our regulations, guidance, and licensing processes to see if adjustments can be made. Thank you for your attention, and I hope you enjoy the remaining presentations. Thanks.
So Jen, I want to apologize right up front for not just writing Virginia Tech. I know that we have some UVA colleagues here that like to point out that all dirt roads lead to Blacksburg. And so I gussied it up just a little bit, but it's a mouthful when you have to say the full name for Virginia Tech, so apologies for that. One of the other things I want to say is I always forget about how much I like coming to the RIC because I get to see a lot of faces that I've not seen in a very, very long time. So for those of you that are out there that know me and that I know you, thank you for coming today. It's really, really good to see you all. So my name is Jason Piotr. I am the New Fuels Team Lead, which was a new position created in the Division of Fuel Management. Actually coming up on 2 years now. In 2021, I took over for the person that was leading the ATF and advanced reactor work temporarily. And here I am, 5 years later, still in my temporary job. So we all know how things have changed over the last several years, and they're going to change more and more. And I think as I get older, obviously, I think time accelerates, and so we'll see what happens. So when I stood here 2 short years ago, our focus was on preparation, building the framework to license next generation fuels. Since then, we've moved on from planning to performance. Today, I'll show what we've delivered, licensing and certification outcomes that demonstrate both our capability and our commitment to the American people. And I'll revisit something that I said then. We are entering a period of rapid change. Little did I know then how much or how fast that change would reshape the landscape that we now operate in. And since I do follow directions and pay attention in class, I'm going to start with the bottom line up front, actually up front. Next slide, please. Chris helped me with that joke, by the way. So in 2025, we completed 106 licensing actions and 14 inspections. Within fuel facilities, we executed 24 licensing actions, and a full 25% of that work involved new or next generation fuel types. We also completed 4 transportation package reviews specific to next generation fuels. Looking ahead, we're preparing for 32 known upcoming actions, all related to next generation fuels. 17 for fuel facilities and 15 for transportation and storage. These are the actions we can confidently anticipate. Based on the pace of change, however, we expect the actual demand to be even higher. Of those 24 fuel facilities, 3 stand out. Next slide, please. First, TRISO-X. We issued a 10 CFR Part 70 license to the first of its kind commercial TRISO fuel fabrication facility, authorizing the processing and use of special nuclear material to manufacture high-assay low-enriched, or HALEU, and tri-structural isotropic fuel, or TRISO. Second, the LES 10 weight % enrichment amendment to support ATF and other LWR deployments with increased enrichment, and the Centrus Phase 3, both of those being important steps in advancing our enrichment capabilities nationally. Alongside these actions, we've realized meaningful efficiencies. We have examples of similarly scoped enrichment amendments, for example, that saw schedules improve from 12 months to 9, and currently estimated at 6 months for some of our current activities that are going on. A full 50% reduction from the first to the most recent review. We revised some of our RAI processes to reduce schedules by roughly 2 weeks, or about 5%, and with further improvements, expect to see additional reductions. And finally, by leveraging past approvals and precedents, such as criticality methodology approvals, we're achieving the same safety confidence with 30% fewer resources. These efficiency gains matter even more given the policy direction and the urgency now driving advanced fuel deployments. Next slide, please. I'm sure everybody has heard about the ADVANCE Act and the executive orders the last 3 days. I do want to point out two that really affected what's happening in DFM. One, 14300, which supports the use of advanced nuclear, including transportable reactors, for national security, climate, and infrastructure, and emphasizes efficient licensing, federal coordination, and supply chain readiness, with a ton of rulemaking work underway on parts of the fuel cycle regulations, including Part 70, Part 71, and for microreactors. Additional EOs focus on deploying advanced reactors, and in particular, Executive Order 14302 aims to reinvigorate the nuclear industrial base. And I want to highlight one example coming from these congressional actions and executive orders. The new fuel pilot line program, which was created to support the reactor pilot program. This includes companies such as Standard Nuclear, Oklo, Terrestrial Energy, TriSoX, and Valor Atomics. In light of this particular project and the expectations that we have from the EOs and the ADVANCE Act, we recently issued a memorandum titled, deep breath, Expectations for NRC Staff Involvement with Prospective NRC License Applicants Planning to Refer the Department of Energy Authorization Process. To explain the NRC staff and DOA pilot line participants and how the NRC will observe the authorization process as part of the pre-application engagements for a future NRC license application. I want to emphasize here that these actions allow for streamlined technical review rather than merely an expedited one. An expedited review will be a byproduct of those streamlined reviews. That will be the result. We hold safety paramount, though, and the work we do with an eye on how we can implement very real, continuous learning behaviors, which will, as another intended byproduct, increase those efficiencies. With that mandate, we continue to build the technical foundation that keeps safety and efficiency aligned. Next slide, please. So in parallel with licensing, we are continuing to invest in the technical foundations. NMSS, with the Office of Research, for example, is sponsoring projects and continues to sponsor projects on near-term ATF, high burnup, increased enrichment, and advanced non-LWR fuels. Our collaboration with DOE, and I want to pay special attention to this one because I think it's very important to our success, is the DOE NRC Criticality Safety for Commercial Scale HALU, or the DNCSH project, which is creating publicly available critical experiments and nuclear data tailored to higher enrichments and novel materials, validating the computer codes that we rely on. And in fact, the third DNCSH workshop is actually happening next week. One of the things that I want to talk about with respect to the DNCSH workshop is that I really believe that things like this, and talking with my colleagues and others in the industry, that this particular activity is a gold standard example for the transparent and coordinated data generation that we need. And we need to use it as a model for the other work that still needs to be done. And if any of you remember talks on this topic previously, we've talked about criticality benchmarks, and we've talked about margins, and we've talked about validation. All of those things are going to be improved by this particular project. But there are other things that we need to take care of in the technical space. And there are other issues that are going to emerge that we will need to treat in much the same way that we are treating these critical experiments to make sure that we can be efficient and effective about doing our regulatory process. One other thing I'd like to mention is that on the back end, we participated in an Electric Power Research Institute, or EPRI, sponsored TRISO-PERT, phenomena identification ranking exercise. And we did that for storage and transportation, again, for TRISO fuel, where we identified continued focus areas. Again, identified critical experiments and benchmarking as an example where additional work still needed to be done, and fuel behavior under transportation accident conditions. The NRC followed up this TRISO-PERT with an activity of our own, which was a post-PERT workshop to communicate results and set the stage for an analogous effort for metal fuels and ultimately molten salts. We expect significant progress over the next year or so in narrowing any technical issues for metal fuels in a similar fashion that was done for TRISO. So what's next as these new issues emerge? Next slide, please. With respect to the front end of the fuel cycle, there remain potential technical challenges for HALEU feed material and near-term and longer-term advanced fuels. As mentioned in the last slide, the availability of those critical experiments and benchmarks for higher enriched fissile material still remains. But those challenges are becoming less of a concern than they were 2 years ago due to the extraordinary level of effort being expended on that particular technical issue. Other areas still under consideration include material control and accounting and security, as well as emerging technical challenges that may be associated with longer-term advanced reactor fuels such as salt fuels for molten salt reactors. I also want to have everyone pay special note to this part. Some external stakeholders, including the international community, have continued to move forward on the back end of the fuel cycle, even at this very early stage in fuels deployment. And we've been seeing questions on this topic for several years now. The NRC will continue to evaluate the regulatory framework and assess information needs to support our readiness for the back end of the fuel cycle, including those potential areas of technical focus such as source term evaluations, criticality and shielding evaluations, thermal performance, and material degradation, considering both short-term and long-term effects. And we'll need to manage all of this amid unprecedented growth in interconnections across the fuel cycle. Next slide, please. As I discussed earlier, we have at least 17 known upcoming licensing activities in addition to the ones for transportation and storage, and that number is expected to rise. Even as we improve efficiency, volume alone demands disciplined day-to-day execution and thoughtful long-term planning. We're engaging with licensees through fuel facility stakeholder meetings, weekly PM calls, and public meetings to identify plans and potential technical issues early. We're translating those insights into realistic budgeting, and we're ensuring contract vehicles are ready and strategically augment staff expertise while we continue hiring. I'm sure many of you have heard that topic come up before. Day-to-day letters of intent, pre-application engagement, and routine interactions are essential, especially for new technologies and new licensees, to produce complete applications and efficient reviews. The level of interconnection between all of these discrete fuel cycle activities cannot be understated. Enrichment of high-assay, low-enriched uranium, for example, clearly drives several downstream activities with separate but linked NRC licensing actions. And often these commercial activities exist alongside DOE activity that can supply some of our advanced reactor enriched uranium needs. Our ability to see and track the big picture and identify which licensing actions are interconnected is an important factor we incorporate into all of our prioritization plans. To close, rapid change is the norm now. Success depends on situational awareness and collaboration that extends beyond formally routine regulatory work. Sustained engagement with licensees, industry, academia, national labs, and government partners is crucial to meet our energy needs in the years ahead. One final thought. Preparation got us ready. Performance proved our capability. Partnership will carry us through the pace of change. Thank you.
Thank you, everyone. I do apologize that I was unable to make the trip to DC. This is my first RIC, and I'm very honored to be a part of this, this very important discussion. You know, one of the things that we focus on at the Department of Energy and the various different laboratories is working together to accelerate and innovate, leveraging the capabilities and the tools that we have available at the laboratories, and that includes advanced modeling and simulation, as well as the experimental capabilities both in our hot cells as well as our test reactors. And what I hope to talk today about is how we're using these tools and capabilities in conjunction with our collaborators to improve and accelerate nuclear energy deployment. So next slide, please. So accident-tolerant fuel, as we've all heard, has kind of been this really interesting inflection point, and ultimately in the United States drove us to this need to have stronger collaboration and coordination between our industry stakeholders, the NRC, as well as the laboratory. In the past, the laboratories have not been as engaged in light water reactor R&D as it is certainly today. And that's really because of the resurgence of accident-tolerant fuel and then its parallel companion in FFRD, which ultimately has broadened the scope, in fact, probably more narrowed the scope in the fact that we've taken things from a system level and we're diving it down into a nuclear fuel component level to where we need to understand what's going on with the cladding and the fuel together as a single component and how things are evolving during the transient. In FFRD, you know, certainly you have to understand things that are going on during the steady state operating conditions, the fuel rod,
Yeah, I know.
behavioral response during that, and then during the transient as well. And what you need to understand, the fuel during the transient will evolve and ultimately fragment and relocate in the cladding and then be dispersed potentially through the fuel rod. And that really necessitated the need to incorporate the modeling and simulation tools that we have at the laboratories.
Cool. There is
leverage
118
capabilities of the experimental facilities. So next slide, please. This brought about the need to ultimately work with industry stakeholders. In this case, the NEAMS program reached out to Southern Nuclear with a proposal to leverage the tools developed in the NEAMS program, as well as leverage the capabilities in the existing suite of tools at the laboratory. This was born out of the fact that there is
already on 18 now. I think
a hybrid core design to support the existing industry. And ultimately, Southern provided these core designs to Oak Ridge National Laboratory, which we implemented into the VERA virtual reactor simulation capability to deplete these hybrid cores and evaluate all of the different pin conditions. And ultimately, this led to the need to remove from a single peak cladding temperature component to looking now at approximately 40 to 60% of the core, depending on what time and condition you are looking at. And what you see here is ultimately the results of these conditions, where we are now looking at all of the high burn-up rods, evaluating when those rods become high burn-up rods, and ultimately the different conditions in which those rods are experiencing things like high rod internal pressures, and what are those contributing factors such as spitting gas release, and incorporating these through a serial process to bring us to where we can understand what local conditions are relevant for high burn-up fuel, which is something that's not been previously done before in licensing submittals. And that's what you see on the right-hand side. So now we have an idea of what these conditions are that we care about. So ultimately that gives us the ability to then test these rods and work with industry stakeholders to get high burn-up fuel from our reactors to our hot cells to do PIE, cut these rods up, and then ultimately do local testing. So next slide, please. This led to the EPRI-CRAFT program being born in, I believe, the 2021 timeframe. And from that, it was really a community to where we could, industry experts could come together, discuss what tests were needed, leveraging things that I showed on the previous slide, and ultimately resulted in this consensus LOCA test plan that you see on the left hand, led by Colby Jensen from Idaho National Laboratory. This was really important, and I think it was really one of the first instances in which you've seen all the different organizations coming together, understanding what conditions we need to evaluate, writing them down in a document, and then using them as a tool to help facilitate the E&E program, in this case the Advanced Fuels Campaign, to target specific tests both in the TREAT test reactor located at Idaho National Lab, as well as the Severe Accident Test Station, also called SATS, at Oak Ridge National Laboratory, which is your historical furnace-style testing. This is really indicative of the need to do more prototypic style testing. A lot of the testing results are built on hypotheticals of a hypothetical scenario, whereas now with this new risk-informed approach, as you've heard from my NRC colleagues earlier today, this brings us to a closer sense of reality. And now that we have the tools and the capability to better understand that, we can now test those realities and gain a deeper understanding of how the fuel is performing and ultimately be leveraged when a vendor and utility request permission to extend burnup. At Oak Ridge, we do our historical furnace-style testing, if you're familiar with Mike Vallone's work back in the mid-2000s, as well as the NRC testing work. These are all very similar components, but what we can do specifically at Oak Ridge is accelerate these things in a way to do more specific testing. What I'm showing here is a picture of a LOCA test specimen where we simulated the impact of a grid spacer, working with Westinghouse as well as some of our other vendor colleagues to understand the temperature conditions that are in and around that scenario, to ultimately understand how the fuel is going to behave at that specific location, which ultimately leads to informing vendor topical reports and how they are able to capture that behavior. And what you see at the bottom are really pretty micrographs that we collect in the pre-LOCA condition. Also, the LOCA condition is the middle figure. But more importantly, if you look at the right-hand image on the bottom right hand, at the location of the grid spacer, you do not see extensive cracking and even pulverization in that form. And what that's suggesting as FFRD is really confined to the material between the grid spacers. Again, this is a very important step that's ultimately helping us refine some of these methodologies that are being used and ultimately submitted for licensing. So next slide, please. So this is, and why is this valuable? And I think this strengthens to the points of the two previous speakers, and the fact that the US NRC drafted this research information letter in 2020, I believe, to really kind of conglomerate all of the information that they knew at this time. Since then, there's not been any development of any FFRD analysis capability, and leveraging the work that the NEAMS program did, the second document here was ultimately drafted using information and output from that that has led to some additional insight by the NRC, and again is being used for topical reports. This led to the PERT, which is the next document, which had a number of laboratory staff included on that to provide expert opinion, leveraging the experimental testing and modeling and simulation capabilities that have been developed at the laboratories. And finally, this draft reg guide that's being ultimately worked on, again, this may be an older version that was provided to me, but it shows that when you look through some of the citations and the references in this document, the work being done at the laboratory is starting to have an impact. And that impact is solely based on the fact that there is closer collaboration between industry partners and the Department of Energy and the laboratories that work under those, and better communication between the laboratories and the regulator, providing that independent R&D and scientific insights that are ultimately helping the regulator accelerate some of their regulatory decision-making process. And this takes us to our last slide, which I promise you we didn't plan it this way, but it's really a carbon copy my version of the previous speaker's presentation, but it's this real idea, it's certainly not new to us, but this idea that we all have to work together. We certainly have our own specific missions between the DOE programs, the industry and the regulator, and we have to maintain independence in a lot of ways. But what we can do is we can work better together, and not at the leadership level. This is even taking from the leadership, pushing it down to our technical staff, working more closely together with the NE programs, with the industry, helping do some of these more cutting edge scientific R&D, such as the modeling and simulation that I showed you previously. And then the DOE can then take those same capabilities and work with the NRC. And that's an example where we provided them the same core designs and information and allowed them to use their tools to understand their capabilities. And then that became a really nice benchmark between the NRC's capabilities and the capabilities developed at the NEAMS program. And in my opinion, for us to really take step forwards, we have to continue driving these collaborations and recognizing that there are forums for these different entities to communicate the priorities, help us understand the gaps. The EPRI craft community is one of those. There's certainly others. And taking that information and becoming very tactical with that and executing on the scope and providing value to the industry. So again, I would like to thank the NRC for giving me this opportunity to talk, and hopefully this will help us have a call to action to work more closely together for a common mission to expand nuclear energy in the U.S. Thank you very much for your time.
Good morning, everyone. It's great to see the level of interest that this topic is generating. I'm really happy to be a part of the RIC this year. My prepared remarks this morning are going to focus on allowable burnup and enrichment as enabling technologies that are unlocking higher capacity factors, fewer outages, and improved fleet reliability for Dominion Energy's fleet, and while maintaining safety margins. Increased burnup and enrichment, together with analytical methods and the licensing changes required to justify them, are advancements that fall under the heading of accident-tolerant features. In this brief presentation this morning, I want to outline how Dominion Energy is using these advancements to transition to 24-month cycles for our fleet, starting with our most technically challenging high-power duty unit, Millstone Unit 3. You'll see this morning how the various components are coming together to bring this about. Dominion Energy's service territory includes the world's largest and most concentrated data center market, with over 5,000 megawatts used by data centers currently. Demand growth in the PJM DOM zone is forecast to increase 5.5% annually for the next decade, with overall electric demand doubling by 2039. New nuclear generation is widely regarded as strategically integral to satisfying this demand, with the goal of providing dependable carbon-free generation. Extending the net generation of existing Dominion Energy nuclear units by transitioning from 18 to 24-month cycles is part of this overall strategy to meet this growing demand. The transition to 24-month cycles will result in increased unit capacity factors, fewer refueling outages, lower operating costs, and improved reliability for customers. The challenge with this transition is not with desire, but instead with feasibility in technical, analytical, economic, and regulatory senses. Core physics margins, fuel performance limits, and regulatory bases must all support the longer cycles. ATF is often associated with coatings or new alloys, but for cycle length extension, the key attributes for economical cycles are higher allowable enrichment and burnup. These changes come with altered fuel cladding behavior, particularly under high burnup, transient and LOCA conditions, which must be explicitly addressed in safety analyses. Achieving cycle energy with acceptable fuel economics requires feed fuel batches to represent well below half of the reactor core. The Millstone Unit 3 core contains 193 fuel assemblies. Reload cycle designs typically involve feed batches of 84 or 85 assemblies for a typical Millstone 3 reload. Without increased allowable burnup and enrichment, to greater than 70 gigawatt days per metric ton uranium and increased allowable enrichment to 6.5 weight percent U-235, feed batches of up to 116 fuel assemblies were calculated to be required to meet 24-month cycle energy and safety analysis requirements. This would result in significantly de-optimized core designs, unacceptable cycle economics, and significantly increased spent fuel management burden. With increased burnup and enrichment, feasible 24-month cycles can be achieved with feed batches as few as 92 fuel assemblies. North Anna and VC Summer will similarly require increased enrichment and burnup to achieve 24-month cycles. Surrey and Millstone 2 have lower power densities, larger fuel pellets and rods, and don't require these changes. Millstone 3, therefore, is first in line, establishing the technical and licensing precedents for fleet application. North Anna, Surrey, and VC Summer will follow. For Millstone 3, 24-month operation drives enrichment needs to approximately 6.5 weight percent and lead rod burnups to greater than 70 gigawatt days per metric ton uranium. This tightens shutdown margin, peaking, and axial shape control, requiring enhanced fuel and absorber strategies. Millstone's transition to 24-month cycles involves increases in procured uranium mass on the order of 15% annually and increased uranium enrichment separative work on the order of 15% annually as well. Supply for these services is limited. Fresh fuel shipments above 5% enrichment changes the transportation licensing envelope. Near-term shipments will rely on exemptions and existing transport availability, while long-term success depends on updated and certified packages and guidance. Fuel cycle and licensing schedules must remain tightly coupled, and a number of challenges to the transition to 24-month cycles remain and are in the process of being addressed. First of all, at high burnup, FFRD, fuel fragmentation, relocation, and dispersal, becomes credible during LOCA or rapid transients. These phenomena affect both cooling performance and radiological release assumptions, and therefore must be addressed directly in safety analyses. Industry approaches are evolving toward risk-informed frameworks. However, Dominion Energy is not pursuing those alternatives for Millstone 3. Instead, Framatome's approach resolves FFRD for the Millstone units within existing regulations, and we anticipate using the EPRI alternative licensing strategy for the other units. Radiological dose consequence analysis is needed to support Millstone 3 transition as well. NRC updates to Reg Guide 1.183 are incorporating higher enrichment and burnup. Spent fuel pool criticality analyses must be extended to support 6.5% enrichment and high burnup. The technical challenges lie in balancing conservative review margins with operational flexibility. Finally, let me talk briefly about the licensing elements of the Millstone 3 24-month cycle project. The Framatome High Burnup Topical Report establishes the basis for high burnup mechanical performance, FFRD, compliance with 10 CFR 5046 for LOCA and non-LOCA accident analysis, fuel performance using Galileo, and core neutronics using Arcadia. The topical report is expected to be approved by the NRC in the first half of this year. The radiological consequences license amendment will explicitly address increased enrichment and burnup and demonstrate applicability of updated alternative source term guidance. The current Reg Guide 1.183 Revision 0 licensing basis does not support 24-month operation with 6.5 weight percent and increased burnup. Accordingly, Dominion is transitioning from Reg Guide 1.183 Rev 0 to Rev 2 and plans to submit the radiological dose consequences amendment under draft guidance, Draft Guide 1425. This is based on extensive pre-application engagement with NRC staff. This approach aligns with the technical direction of the revised source term guidance while maintaining schedule alignment with the 24-month implementation. In parallel, Dominion will submit a spent fuel pool criticality license amendment to support receipt and storage of high enrichment, and storage of higher burnup fuel. This amendment will implement any required rack loading restrictions and regional storage constraints to maintain subcriticality and as a prerequisite for receiving LEU plus fuel on site. Resolution of LOCA and high burnup fuel fragmentation, FFRD, is addressed within the fuel licensing basis using the fragmentation methodology. This method explicitly treats FFRD across all brake sizes and remains within the existing 5046 framework. Fuel-related technical specifications and core operating limits report changes will integrate the approved fuel limits and analytical methods into the operating license, including fuel melt limits and any millstone-specific restrictions for burn-ups greater than 62 megawatt days per metric ton. Balance of plant impacts are addressed through a generic letter 9104 license amendment. This covers surveillance interval alignments, instrument drift over extended duration cycles, and associated risk-informed justifications. Finally, transportation and fresh fuel shipment licensing supports initial LEU plus delivery, relying on interim exemptions until fully licensed shipping containers are physically available. From a schedule standpoint, the spent fuel pool criticality amendment is targeted for July of 2026 submittal. The combined radiological dose consequences and fuels amendment is targeted for submission in September 2026. And the generic letter 9104 amendment is targeted for submission in November 2026. Completion of these actions supports Millstone 3's first 24-month operating cycle starting in spring 2028. And again, this is Dominion Energy's highest power density core and among our most challenging. Framatome's effort for increased enrichment fuel fabrication at their Richmond facility they're on track to support Millstone 3 fuel fabrication in 2027, and Millstone 2 will follow suit with its first 24-month cycle starting in spring of 2029. So in conclusion, our efforts at Millstone will establish the path that can be replicated across the Dominion Energy fleet and provide sustained plant reliability and economic benefit. Thank you.
All right, so I want to thank all of our speakers. I definitely learned something. And now we will move on into the question and answer portion. So if you haven't already, I see some of you have, go ahead and scan the QR code to add questions to the queue, and we will go through. So I think our first question here is for Chris. New fuel forms will have advanced cladding and non-zircaloy cladding. Will the 10 CFR 50 fuel regulations be updated to go beyond zircaloy conditions during accidents and limits?
So I think for some of this, it depends on what we're looking at. If an applicant comes in with a very unique design that we don't have our own information, or that we can build ahead of time, I think the appropriate path might be an exemption in their case. For something that's maybe a little bit more of an interest throughout the industry, early engagement is highly encouraged, and I think we can use that early engagement period to figure out where we can revise the rules as necessary. And I think it's, to some extent, maybe not the most satisfactory answer. It'd be nice to be able to tell you exactly what we're going to do, but in the end, it all comes down to what the design is. So hopefully that helps, and please catch me afterwards if you'd like to hear more about it.
All right, thanks, Chris. Next, we have a question that was directed at Nathan. So what are some examples of successful DOE NE programs that have positively impacted the nuclear sector and helped drive industry growth?
I think you don't have to look any further than the accident-tolerant fuel program. It's been widely one of the most successful programs that I'm aware of, certainly not aware of all of them, but certainly speaking with both vendors, the NRC staff, as well as the utilities, it's been an opportunity for expansive R&D growth and strategic discussion. It's led to both FFRD, and now more recently power uprates, and continuing this program, perhaps with the success of the implementation of accident tolerant fuel, we will continue to grow the light water reactor R&D in the U.S. and continue to deploy more nuclear energy for the country.
All right, thanks, Nathan. This one was directed to John. To facilitate the 24-month refueling cycle, is Dominion primarily looking at conventional oxide fuels with increased enrichment and allowable burnup with no accident tolerant characteristics, such as dope pellets or coated claddings?
Yes, that's right. We're not going to be using coated claddings or dope pellets in the transition to the 24 months.
Thank you. This one was directed to, I guess, NRC staff. Let Chris take a first stab. So given recent staffing challenges across federal agencies, how will NRC and DOE sustain timely, high-quality collaboration?
So in terms of collaboration, actually that's a very timely question, because normally at 1 p.m. this afternoon we would have had our regularly scheduled DOE NRC management touch point. So we obviously postponed that because of the RIC, but we try to maintain regular touch points between the two government agencies. In addition to that, on a technical level, we also participate in multiple things together. One example that I can come up with is my previous participation in the Accelerated Fuel Qualification program, our working group, which was a collaboration between NRC, DOE, and industry to kind of flesh out the areas that we thought could be improved in the fuel qualification process. So through those types of things, both technical and management, we do our best to keep coordinated and use our resources the most wise way we can come up with.
Thank you. This one is for Nathan. What modeling and simulation tools are currently being used for LOCA prevention, and how are they being implemented in the industry?
Well, I can't speak necessarily to what the vendors and utilities use, so I'll focus predominantly on the DOE NE tools. So the NEAMS program develops VERA as well as the Bison Fuel Performance Code. I know, certainly Constellation and Southern Nuclear are the two that I'm most familiar with, use VERA as confirmatory tools for their own internal core designs and safety calculations. I'm also aware that Bison is utilized to do PCI analysis at Constellation. And I'm also aware that I believe Kairos Power has licensed Bison for use in their advanced reactor. I know that's not the same forum, but I think that's an important thing to highlight as a success story for the fuel. So it's predominantly used for confirmatory analysis and even some methodology development. But to my knowledge, it's not being used for any licensing applications, just confirmatory assessments.
Thank you. So this is directed to NRC staff, and I think, Chris, again, you get to be first up here. So with the national labs performing testing of so many ATF and traditional fuel rods right now, what is being done or could be done to get the results into the hands of the NRC staff?
So I think it also depends maybe on that data, what it was collected for, but one of the primary examples of how we collaborate to get that information is the Office of Research has a memorandum of understanding with EPRI, and so whenever there is data that is collected, sometimes that will be incorporated if it makes sense into our confirmatory tools. If it's direct from the national labs, we usually participate as appropriate with the labs in pre-meetings, so we understand what the testing is going to be, how it will be performed, how it can be used afterwards, and so we're kind of embedded in that process as well. So,
is there anything different in NMSS space?
I don't. This is working? My green light's not coming on. I don't think so. And I'll go back to what I was saying earlier about the DNCSH program. I think what we have to maintain is an awareness that there's a lot of things moving, including staff at a variety of locations. And so If you don't maintain those sort of anchor points like that particular program, it would be difficult to maintain the interactions and connections. So we have to be assertive about the way that we go about sharing information and collaborating on these things, and we have to be continuous about it. If we let any gaps occur, then that's what happens is that people leave, and then you don't really understand what's going on anymore. So again, I think if we put together programs like the DNCSH and make those things durable good, it's going to help us with all of the flux that we have, not just in staffing.
Thank you. So this next one is also for you. How will the new Part 57 and the existing Part 71 work together for the safe transportation of microreactors in the future?
So Part 71 is going to be still the main driver for transportation packages. There is a linkage between the two, and clearly there has to be. But the thought is that we didn't want to necessarily reinvent the wheel, and so there are aspects of Part 71 that are absolutely fantastic to be able to regulate transportation of nuclear material. And so they're going to work in concert with one another rather than being separate and apart from one another.
Thank you. So this one is for John. Fuel cycles have been extended year by year, but how far can we extend them for existing light water reactors? Is more than 24 months also included in the scope for the future?
At this point, I have not seen evidence of going beyond 24 as being feasible. The boundaries that are placed around this, everything has to work together. The technical capabilities of the fuel from a fuel performance perspective, the economic feasibility, the regulatory support, all have to come together. And so it's a very designed problem to ensure that we are able to go further. So at this point, I have not heard of anyone speculating going beyond 24 months for the legacy units.
And I think you touched on this in your presentation, but somebody asked, why is Millstone 3 first? Because it's a merchant plant?
No. Millstone 3 is first because it has, it's large generating station, 2-unit, and 2 units of different design. And we saw the opportunity based on technology that Framatome was bringing in terms of how the FFRD was being evaluated. We saw the opportunities to utilize the increased enrichment and their fabrication capabilities at Richland to be able to reliably get to 24 months by the time the calendar hit. And let me say what I mean by that. That we have, in taking the entire fleet to 24-month cycles, we had to look at the integrated outages, and when you move one, you have to move the second. And so you have to kind of look at how you're operating as a fleet to determine what optimally will do this. We did see, because of the technology that Framatome was bringing, is that we had the opportunity to attack this most challenging unit. And it's in terms of its power density, it's a large core and highest power density in the country. And we said, let's attack this, and took it on as a significant challenge so that we really could pave the way for the rest of the fleet.
Thank you. And then a somewhat related question for you again, John. How are the increase in discharge fuel associated with 24-month cycles and the increased spent fuel pool restrictions imposed by criticality analysis impacting spent fuel and dry fuel storage management?
Yeah, that's a great question. So of course, we're having to look ahead for spent fuel management. There's just so much throughput that an operating utility wants to do in terms of dry cask storage projects in any given calendar year. So we did look out ahead to see what kind of pool impacts there would be in terms of having to, the criticality analysis is going to have to zone, identify the zones in the pool where it's feasible to discharge the various designs, the various levels of burnup. And then at the same time looking ahead for dry storage. So the opportunity we have now is to actually do integrated spent fuel pool management and dry storage management to look very selectively at candidates to do both pool management and dry storage management in coordination. So that's an initiative that we've taken on internally to make sure that we are we don't have, we have laminar flow as we go through this process. We don't want to have turbulent flow as we go through.
Thank you. And somewhat related to Jason. So what work has the NRC done to research challenges or complications associated with higher burnup fuels for long-term storage of the spent fuel after being removed from the core?
So I mentioned that we have significant amount of research going on with the Office of Research that does relate to back end of the fuel cycle. So trying to remember, I just lost it. I had it and I lost it. We have a program and it's Volume 5. That's what I was thinking of. So Volume 5 is part of our strategic plan for looking at all of these different various changes with the fuels and what's happening with the higher burnup, with the increased enrichment. As part of that Volume 5 work, we do a significant amount of work with research to make sure that we have the information that we need to be able to regulate that properly.
Thank you. And then continuing on, you talked about back-end work, but you haven't said anything explicitly about reprocessing. So how is the NRC addressing that?
So I took a couple of notes here. My normal list for the back end and areas where we need to work on making sure that we close technical gaps has really focused on triso metal and MSRs. I added to my list just now that reprocessed fuels need to be added to that list. And so I'll speak to it from the perspective really quick about the commonality being is that we don't know what the final fuel forms are going to be. We don't know what it's going to look like in terms of what the commercial output is going to be. And so while we're preparing for those things, certainly on the back end of the fuel cycle with respect to LWR fuels and some advanced reactor fuels, it's a real challenging problem until you know exactly what those fuel forms or those waste forms are going to be. And it's not that we're not thinking about it, it's that we're prioritizing where we are in the process and where we are in deployment. We will be working on that, and we are working on the reprocessing aspect of it. I will note that as recently as 2021, the staff discontinued rulemaking on reprocessing because there was not an interest in the industry to move forward with reprocessing, and at the time, even for advanced reactor fuels. Much like I said in my talk, things change rapidly, and we are now in a space where reprocessing has really come to the forefront, and so we'll be looking very, very hard at that, just like we did with all the other fuel forms that we've been looking at.
Thank you. I thought we had a question here for Nathan, but I don't see it now. Okay, here we go. So I think we maybe touched on this a little bit already, but Nathan, did you have any additional thoughts about how DOE, any programs can collaborate more effectively with industry to accelerate growth in the nuclear sector?
Yeah, that's a good question. And certainly I kind of highlighted that at the end of my presentation. It's certainly a challenge. The NRC needs to maintain the trust of the public. So, it becomes challenging to have direct engagements, but the DOE-NE, in my opinion, needs to be seen as an independent R&D organization. Now, that doesn't mean that we can't work with the industry. We can certainly identify high impact problems that we need to work and even develop strategies to tackle those. But we ultimately need to be able to go back and collect that information in an independent way. And that allows us to then approach the NRC and provide that data and give the NRC confidence that it is independent. Conversely, we need to be able to work with the industry stakeholders to attack these problems that are challenging and be more effective in that role and be responsive to the industry needs. So I think that's just a little bit more context to some of the thoughts that I had laid out in my slides. Hopefully that helps address the question.
Thank you. Another question for the NRC staff. What efforts are being conducted to advance molten salt fuel qualification?
So for that one, yeah, it's absolutely true that molten salt reactor fuel is quite a bit different than our traditional fuel forms that we see. And yeah, I want to point out maybe a couple of different new regs that help in that process. So the Division of Advanced Reactors had previously released a new reg 2246, I believe, on fuel qualification for non-LWRs. While that one goes a long way and it provides a more top-down approach to fuel qualification, it is really more based on solid fuel forms. So with that in mind, we had partnered up with Oak Ridge, and I think I earlier saw Dave Holcomb here. Yeah, there he is. So yes, we have the author in the room here. So Dr. Holcomb had worked with us to develop a fuel qualification guidance to kind of bridge that gap between what we had for New Reg 2246 to what would really be needed for molten salt reactors. If I recall correctly, I think that's 7299, but I'm not 100% sure on that number at this point. So, but yes, we do have two new regs that would assist in fuel qualification for molten salt reactors.
Okay, and then another one for John. What is Millstone's timeline for ATF implementation? Is the chain of license amendment requests presented all separate LARs, or is there going to be a combined LAR?
Yeah, let me pull up my notes here, make sure I get it straight. So we've got a high burnup topical report. That's first half of 2026 approval, so that's already submitted. The spent fuel pool criticality license amendment is a separate amendment. That's July 2026 submission and mid-2027 approval expected. The combined radiological dose and fuels license amendment is September 2026 submission, so September of this year, about 6 months, and 1 year approval cycle for that. The balance of plant, which includes all of the plant-related changes for surveillance intervals and that sort of thing, that's targeted for submission at the end of the year and then approval by the end of 2027. And so then Millstone 3's first 24-month cycle will begin in spring 2028 and Millstone 2's in spring 2029. So then they'll be on opposite year implementations so that we'll only have one outage per year for each plant.
All right, thank you. To Chris, can you summarize the basis for your statement that dope fuel has lower fission gas release during accident situations?
Okay, so for this one, you know, some of it maybe is more in the theory versus some of the test results, but in theory, for the doped pellets, what we're looking at is larger grain sizes, and traditionally fission gas, particles will escape via the grain boundaries. And so the idea and the concept is that with the larger grains, we're going to have less pathways for fission gas to release. Of course, what you start out with and what happens during an accident can change. So maybe the grain boundaries don't stay large, or maybe other things happen. But and honestly, I would say maybe Nathan could even weigh in on that if there's additional info from the labs on some of those test data that's out there.
Nathan, did you want to chime in?
Yeah, I think Chris is on point there. We are working to collect the data. We've received second cycle fuel, so that's going to be rod average 55. We'd call that your standard high burnup fuel. We're expecting to receive some of that material at Oak Ridge as early as May to do some testing, and we intend to collect transient fission gas release data from those results. And I believe we have third cycle material planning to be shipped to Idaho either late this year or next year. And that will be your high burnup fuel, ranging from 72 to 77 rod average burnup, so very high burnup. And we will collect that data to support the theory that is very strong that Chris has laid out for us.
Thank you. This one's for Jason. Do you feel that the regulations need to be updated or altered to support reprocessing facilities?
So I think that's still an open question, at least to some degree. I know when they discontinued the rulemaking back in 2021, they looked at what the pathways were, whether it was a Part 50 pathway or whether it was a Part 7X pathway, either Part 70 or perhaps a new regulation. So we're still looking at that, and you know, as we move through the process of seeing what's going to be coming, we'll make those determinations.
Thank you. And then also for you, what were the major safety or interesting issues for the 10% enrichment at LES?
I think criticality safety is the main one that you're going to look at when you're talking about the increased enrichment piece. You know, as I mentioned before, we talked about critical benchmarks and having you know, enough critical experiments and benchmarks in place such that you can perform an efficient and effective review. And so as you increase enrichment in any of these facilities, you're going to have to look really, really hard at the criticality safety piece of it. That being said, when you start looking at perhaps other fuel types or other fuel forms, there may be other things like chemical process safety that you have to look at as well.
Thank you. We have time for a few more questions. So Chris, the initial draft of Rev 2 of Reg Guide 1.183 supported enrichment up to 10 weight percent. What's the driver to support up to 20 weight percent, and what work or research supports the extension?
So I think the driver is just looking ahead and recognizing what the industry might be going to in the future. But as far as what has been done by research, I will fully admit that there's less data the higher up you go. But there is some data that we've been able to leverage, and so we're incorporating that. I am aware also that there's an effort underway right now by ANS to look at the standard, ANS 5.4, to see if there's an appetite and enough information to update that standard as well. So it's an ongoing effort, us, the industry, research as well.
And then I think also for Chris, how are these enabling fuel technologies being used in space initiatives in conjunction with NASA and the space industry in general? What's NRC's involvement in the process, and how is it benefiting the space industry?
So for the most part, I'm not aware of too much from especially the operating fleet, LWR fuel being used in NASA applications. I am aware of some of the advanced reactor non-LWR fuel forms being somewhat related, and so where there is an overlap, we would reach out, or they would reach out, whichever the case may be, to better leverage the data and the knowledge that has been gained. I almost want to say that maybe Nathan could weigh in a little bit, because I know there's more work done by DOE, and in particular, I know that there was a kilowatt reactor that was supporting some NASA work. So the NRC is not as tied in with NASA, because I think there's a pretty big difference in our fuel forms and our reactor designs, but DOE, of course, it would be more of a resource for NASA.
Yeah, Chris, I thought we agreed to make sure you had all the hard questions, so I'm glad it came through. But I'll do my best to answer the question. So I'm not a space reactor guy, but the program that I manage develops the TRISO particle under the AGR program, and as we're progressing that, it's moving more to particle fuel R&D, and I'm certainly aware that a number of the space reactors are considering TRISO fuel as one of their components. R&D is underway. I believe the AGR TRISO particle has been submitted or is being submitted soon to NRC for review, and they should be wrapping that up in 2 years, so that will be qualified for domestic use, perhaps not terrestrial use. I'm not sure how that would work, but there is work being done. We work closely with NASA and some of the other companies to develop those reactors and implement new technologies, but it's certainly an inherently different technology than what we're considering for light water reactor fuels.
Thank you. So I think we have time for maybe one more, and then we'll get out of here on time. So this was for John. Did Millstone take advantage of, or do you plan to take advantage of pre-application audits for the ATF-related LARs?
So at the discretion of NRC, yes, we find that the audit process works very well. This is an opportunity to come in and have a really open dialogue and exchange, clearly get the questions to the root of the question that's being asked. This has been a very effective process for us. So yes, we would certainly entertain that for this and for any future applications.
All right. Well, I want to thank everyone in the audience today for coming to learn and for your active participation in getting us all of these questions for our panelists. And again, thank everyone on the panel for giving us your time and your knowledge today. Thank you so much.